con los terroristas.
We are getting ready to find derivatives and antiderivatives of exponential and logarithmic functions. So before we do that, you need to review a few things about what an exponential and a logarithmic function are. They are inverses of each other, which we'll get to in just a little bit. Before we get there, let's go ahead and review some of the things that you may remember. First, what is a function? The easiest way to describe a function is for each input, there is only one output. So for each input, there's only one output. And how do you tell, and you may remember from Algebra 1 and maybe even pre-algebra and all the courses after that, we can tell that something is a function if it passes the vertical line test that you are very familiar with. Next, what does this mean? When you see f with a -1 of x, this does not mean it has a negative exponent and you'd move it to a denominator of a fraction. This is, as you probably remember, the inverse of f of x. So this is f inverse of x, or the inverse of f of x. Last one is, what is meant by a function being one-to-one? A one-to-one function, you may remember, is a function that for each input it only has one output. So it is a function. It's definitely a function. And it also is a function with respect to y values, which is kind of crazy, but for each y value, only has one x value. So you can think of that being a function. So each x only has one y, and also each y only has one x. That is considered a one-to-one function, and we'll review what that is graphically here in just a second. What kind of test do you see? If it is a function, we went through that, that is the vertical line test. What kind of test would you do to see if it is a function that is one-to-one? So first, we know it's a function if it passes the vertical line test. And if it is one-to-one, it must also pass a function test horizontally. For each y, there's only one x. So it would pass the vertical line test and also the horizontal line test. So if it passes the horizontal and vertical line test, we know the function is one-to-one. So, looking at an example or two. If our function is x cubed, is that one-to-one? Well, we know x cubed looks something like this. Now, does it pass the vertical line test? We know that it does. It is a function. So, yes, it passes the vertical line test. Then you're checking to see if it passes the horizontal line test, which it does. So we know this function is one-to-one because it passes the horizontal and vertical line test. Check out x squared. First, is it a function? Yes, it is a function. Now, is it a one-to-one function? It would have to pass the horizontal line test. Well, if we think about x squared, we know that that is a parabola looking something like this. Does it pass the horizontal line test? No, because it intersects in two places. Or this y value has more than one output on the x value. Or there's more than one x value that give you this y value. So no, it is not one-to-one. It is not a one-to-one function. That will become important when you learn in just a couple of minutes the formula for finding the derivative of inverses. Continuing on with review from your one-to-one functions. One-to-one functions have inverses that are functions. So we know if something is one-to-one, it is a function, and also its inverse is a function. That becomes important. If f is a one-to-one function with a domain A in a range B, then its inverse function has a domain B in a range A. Remember from our work with inverses that if I know a function, and I'm just going to draw our function clouds here, if 4 maps to 8, and this is our original function, then I know the inverse would undo what was done. This would be our inverse. 8 would map to 4. So this is our original domain and range of our original function, f of x. The domain is 4, the range is 8. But on the inverse, it undoes it. Our domain is 8, and our range, or our output, is 4. So the domain and range just switch for two functions that are inverses. How do you find the inverse of a function? This is something that we have done a million times, and you probably can do it very quickly. In order to find the inverse of a function, and I can hear all of you screaming, you switch the x and y, and then solve for y. So switch the x and y, solve for y, and then you'll write the final answer in our inverse function notation. So let's go ahead and maybe look at an example of finding the inverse. So here is our original equation, which f of x, which is also y, equals x cubed plus 2. Now, first step, switch the x and y. X equals y cubed plus 2. Solve for y. Cube root of x minus 2 equals y. This is our inverse of the original. And then we'll just write it in our function notation. The inverse of f of x is the cube root of x minus 2. These two things, you should see the relationship for their inverse. This function cubes x and then adds 2. Our inverse should undo that. This one subtracts 2 and then cube roots it. So it's undoing what the original function does. That's what inverses do. Inverses, graphically, you may remember the relationship. We know that inverses reflect across the y equals x. So if this is our original function, x squared, the inverse will reflect across the line y equals x, and you'll have, that's a horrible drawing, but you'll have a function that is an inverse that looks like this. In this case, since it's not one-to-one, our original, our inverse is not a function. One-to-one functions, like x cubed, have inverses that are functions because they are one-to-one. The inverse is a function because it's one-to-one. Alright, last but definitely not least, you can draw the inverse in a calculator. If you enter your function into y equals, so let's say you have y1 is x squared, you can go to the graph and then hit the draw button. So you're going to hit second program, and then if you go down to number 8, it says draw inverse. And then it will have this. If you're on the home screen, you can enter this and then just put y1, and then it will take you to the graph and it will have a sketch of the inverse of this. All it's going to do is reflect it over the line y equals x. So this is just another calculator command that you can use if you need to see what a picture of the inverse would look like. Let's take a look at what some of these inverses look like if we're given values. So first I'm going to take a look at this first part, and I'm going to draw a picture to help you realize what's actually happening here. We know that f of 1 is 5. That means if I have our functions, if this is the domain A and the range B, the function, when I input 1, maps to the point 5. F of 3 is 7. That means the function, remember this is f of x, so f of 1 is 5. F of 3 is 7. F of 8 is -10. That is what this first part tells us. This is the visual of that information. If I input 1, it outputs 5, domain range. Now, if I want to find what happens when I input 7 into the inverse. Now remember, inverse is undo. It switches the domain and range. So if I input 7 into the inverse, just going to make this a little smaller. Here's our inverse. I'm going to go ahead and do some crazy function blobs for our inverse. If I input 7 into our inverse, remember it undoes what we previously did. Well, 3 mapped to 7, so our inverse must have 7 mapping to 3. This is the inverse of f of x. The next one, find f inverse of 5. So if I input 5 into the inverse, it's going to undo and it will map to 1. And lastly, if I input -10, it will map us back to 8. This is a good visual for what inverses do. If I input 1, it maps to 5. If I input 5 into the inverse, it will map us back to 1. Now to a calculus theorem that you will need to know. It will be in your brain. This right here is the formula. We're going to discuss it and kind of talk our way through it and what this means. But you need to have this in your brain. So upon watching this video, read it 3,462 times until you have it in your brain, because you will need it whenever you're trying to find the derivative of an inverse. Alright, let's take a look at the definition first. And as usual with calculus definitions, you are given some pre-existing things that must happen in order for this to hold true. First, if f is 1 to 1, if it is 1 to 1, if our function we're given f is not 1 to 1, none of this is true. So it has to be 1 to 1. It also has to be differentiable. You have to be able to differentiate the function f for this to work. If it's not differentiable, then none of this is true. So it has to be 1 to 1 and differentiable with, now we'll get to some of our definition here. The inverse function is g. So g is the inverse of f. So g is the inverse of f. And this f prime of the inverse of f cannot be equal to 0. And you can see why, because our denominator of this fraction cannot be 0. Then we have explosions and all kind of crazy things happening. Cannot be 0 in the denominator. Then the inverse function is differentiable at a, so we know it's differentiable if these things are true, and we have the formula to find the derivative. Now, let's talk about what this left side is. This is g prime of a. Remember, g was the inverse, so you can think of this as being the inverse's derivative. This is the derivative of the inverse is given by 1 over the derivative of the original function, f prime, but this is kind of like composition. It is composition, in fact. You will have to input in g of a. Now what was g? G was the inverse, so we have to input into our inverse the a value. And then we'll have the derivative of the inverse. This definition is very important. You must make sure these things are true. If they are not true, this does not hold true. This is our derivative of an inverse. Know this formula. Circle it, star it, highlight. Here's our first example. We're given the function y equals x squared. That's the same as f of x equals x squared. And we are given a domain. We want to find g prime of 1. Now remember, based on our previous definition, that g is the inverse of f. We want to find that derivative at 1. So the slope of the inverse at x equals 1. That's what we're looking for. Slope of the tangent of the inverse at x equals 1. So there's a lot going on here. Now, first of all, it must be 1-to-1 and differentiable. The way we're given this, we're given it from 0 to 2 for the original function f of x. On this domain, our function is 1-to-1. If we look at this graph, at 0 it's 0, and at 2 it's 4. This is the domain we're given. We have a restricted domain, that way our function is 1-to-1. Now, since it's 1-to-1 and differentiable, we can apply our formula. And I have the formula over here on the board. The derivative of the inverse at 1 is given by 1 over f prime of g of 1. Remember, g is the inverse of f. So let's go ahead and try to find some of these things. First thing we need, we're going to need the derivative of f in order to simplify this equation. So I'm going to find that. F prime of x is equal to 2x. That should be very, very simple based on the math that we've been doing up to this point. Now, if I'm finding g prime of 1, it's equal to 1 over the derivative of f with g of 1 plugged in. Now, what is g of 1? Well, we would need the inverse of this function. So we know that g of x is given by the inverse of f of x. The inverse of f of x is, if I'm looking at this, I can solve, it'd be x equals y squared, or plus or minus square root of x equals y. Our inverse is this. Now, we have a restricted domain, so we're only dealing with x values that are between 0 and 2. So we know it's going to be positive. So if this is our inverse, g of 1, or our inverse at 1, g of 1 is going to be the inverse at 1, which is the square root of 1. So g of 1 is 1. G of 1 is 1. Now take a look at what that's going to look like. If g of 1 is 1, the inverse evaluated at 1, it's 1 divided by f prime with g of 1 plugged in, which is 1. The inverse of f of x at 1 is 1 over f prime of 1. We know f prime of x, so I can plug in f prime of 1, which is 2 times 1, which is 2. So it's 1 over 2. The slope of the tangent of the inverse of f of x at the point x equals 1 is 1/2. Here's our second example. We're given a function f of x, and we want to find the derivative of the inverse of f of x at 1. So we can use our formula as long as a couple of things are true. First, is this differentiable? And you could look at a graph or just know that I have some number plus cosine. It's going to be a constant. There are going to be no asymptotes. There are no places where it's undefined. This is a continuous function that is differentiable. The second thing you need to do is decide whether it is 1-to-1. Now there's a little trick that we can use to show something is 1-to-1. What is the derivative of f of x? F prime of x is equal to the derivative of 2x, 2 plus the derivative of cosine, which is negative sine, which is 2 minus sine of x. Now this is the derivative. And I would hope that you agree that this is always a positive number. If our derivative is always positive, we know that the function is always increasing. Let's talk about why I know the derivative is always positive. It is 2 minus some sine value. We know sine is always in between -1 and 1. So 2 minus that value, it's never going to get to 0 or less than 0. So we know that f prime of x is always greater than 0 or positive. Therefore, our original function is always increasing using the first derivative test. If you want to sketch what that could look like, if something is always increasing, I have no clue what the graph is looking like. But if something is always increasing, it must always pass the vertical and horizontal line test. So using that knowledge, we have just shown that the function is one-to-one, and we have said it's also differentiable. Therefore, we can use our formula, and I'll write the formula down and then we'll go to work. Alright, our formula. The inverse of f of x's derivative is given by 1 over f prime with composition f inverse of x plugged in. So I want to evaluate it at 1. We can do that. Here we go. The inverse of f's derivative at 1 is given by 1 over f prime of f inverse of 1. This is the formula that we are going to be simplifying and finding. Now, what do we need in this formula? We need the derivative of f, we have it over here, and we need the inverse at 1. Well, we can find that value. What you're looking for, if we're thinking about our function blobs, this is our domain and range, and if I'm thinking about a function value, f of x, it should map to 1. I'm looking for the number that when I plug it in, it maps to 1, because then 1 must map back to that number for the inverse. And it just so happens, if you use a calculator or a little logic, if I plug 0 into here, it would be 0 plus cosine of 0. Cosine of 0 is 1. So 0 maps to 1 on the original function. Therefore, the inverse, f inverse of x, of 1 gives us 0. So we know this value, f inverse at 1, is 0. I'm going to continue. So it's 1 over the derivative evaluated at 0. That is something we can find because we know the derivative. So it's 1 over the derivative evaluated at 0, which is 2 minus sine of 0. Simplifying further, 1 over 2 minus sine of 0. We know that sine of 0 is 0. Our answer for the slope of the inverse at 1 is 1/2. That is all for our lesson on differentiating inverse functions. This formula is one that you will know from now on. Have that formula in your brain. Find the derivative of an inverse, state it's 1-to-1, state it's differentiable, then you can use this formula. We'll continue on in the next lesson.